Very well, I'm now recording. The new chapter that we started and we continued a little bit was regarding the Fourier series representation of periodic signals. So what was the representation? We were having a periodic signal, x of t, as a summation of scaled complex exponentials. For example, a1 times e to the j omega 0 t. This omega 0 is the fundamental frequency I'm talking about. And then we have plus a2 times e to the j 2 omega 0 t plus a3 times e to the j 3 omega 0 t plus blah blah. Of course, plus we have a minus 1 e to the minus j omega 0 t plus a minus 2 e to the minus j 2 omega 0 t plus etc. So both the negative multiples, integer multiples, and the positive integer multiples of a fundamental frequency will form all types of, almost all types of periodic signals. There are, of course, some conditions where sometimes this does not work. If, for example, there are too many or infinitely many discontinuities of a signal within one period, or if it makes infinitely many oscillations within one period, or if the value of the signal diverges to infinity and things like that, they are, of course, clearly violating this capability. But for normal signals that you can draw, of course, this representation is valid for periodic signals, of course. And there must be a fundamental period of that periodic signal, and everything must be multiples of that, integer multiples of that. All harmonics must be integer multiples of that frequency. So we do not have a fractional type relation between two harmonics. That's sometimes critical because in some of the cases, it means that you're supposed to determine first the fundamental frequency. That's important. Let me ask you a question as an example here. So the example is x of t is equal to a times cosine 2 pi over 5t plus b times cosine. Let's make them cosines because we know that the Fourier series coefficients for these are real. They are 1 over 2 times the scale, of course. Otherwise, for sines, or if there is a phase difference, you will have to take into account those phases in the form of complex numbers. But that's not what I'm trying to show now. I'm talking more like, what is the fundamental frequency here? For example, x of t is equal to a times cosine 2 pi over 5t plus b times cosine 2 pi over 6t. First, what are the periods? What is the fundamental period? And what's the fundamental frequency of this summation? There may be more than 2, of course. It may be just very long, arbitrarily long, infinitely long. But what is the fundamental period? Therefore, the fundamental frequency corresponding to this one. The frequencies, individual frequencies, are here. This one is the frequency of one of the cosines, and this one is the frequency of the other cosine. But they are not the same, so we are summing them up. Did I receive some audio? I just couldn't hear. You may repeat if you have a question or if you have an answer to this one. Or if it's a mistake, then I will continue. Here, you may think either way. I find it a little bit easier if it is given already in this format, like if the periods are eminent in these terms. The periods are eminent. 2 pi over that thing is the period. So, for example, t1 is 5. The period of one of the cosines is 5, and the other one is 6. So what is the period of the summation then? We know that it is the least common multiple. We know it from periodic signals, periods of periodic signals. So from here, we deduce that t is equal to 30, 5 times 6. That's the least common multiple. Sometimes if they have common denominators, then of course the least common multiple will be maybe smaller. For instance, if T1 is 4 and T2 is 6, then the least common multiple is 12, right? It's not 4 times 6, which is 24, but it is half of it, 12. So these two periods must reach to this period, to T, which is capital T, which is 30 for this case, by an integer multiple of your described period. So there is an integer multiple that from where, from T1 is equal to 5, you will reach to 30 by just multiplying with 6. And same is valid for 6, because then you have to multiply it with 5, which is an integer. If these are fractional, for example, you have to be very, very, very careful. For example, let's say one of them is 2.5, okay? Or, even 3.1, okay? They would complicate things a lot, and you have to be extremely careful to find the fundamental period or the frequency. Here I found the fundamental period, but this was an easy example. And it is 30, but still it shows you that you have to be careful. This is the fundamental period, and therefore the fundamental frequency, let's call it omega 0, is equal to 2 pi over 30. This is the fundamental frequency. Now we know that x of t can be written as a over 2 e to the j 2 pi over 5t plus a over 2 e to the minus j 2 pi over 5t. I'm sorry for the mess, it's just making a mess, so let me separate it a little bit. Plus b over 2 e to the j 2 pi over 6t plus b over 2 e to the minus j 2 pi over 6t. Now be careful here. What are the Fourier series coefficients? First of all, I can see the Fourier series coefficients. They are a over 2, a over 2, b over 2, and b over 2. I can see 4 distinct Fourier series coefficients clearly. But what are their indices? What numbers are they? What indices are they? For example, is this, let's say, C1? And the answer is, strangely, no, it's not C1. Or this one is not C1 either. Okay. So I'm erasing them. This is not correct. The index must be according to the fundamental frequency. So you have to define or find, for example, 2 pi over 5, that's this one, that one, as an integer, k times the fundamental frequency. What was the fundamental frequency? It was 2 pi over 30, right? It's here. So 2 pi over 5, that frequency of the harmonic must be an integer multiple of the fundamental frequency, and it is indeed. What's k here? It's 4. K is equal to, k is equal to 6. So I have to write everything as an integer multiple of the fundamental frequency, which is 2 pi over 30. So I will write this thing again. Of course, I have to do for the others too. For example, what is 2 pi over 6? 2 pi over 6 is equal to k times 2 pi over 30. And here k is equal to 5. Okay, I have to think of it that way. So I will write x of t is equal to a over 2 times e to the j times, for instance, 6 times 2 pi over 30, that is omega 0, by the way, t, plus a over 2 times j times, oops, what am I saying? E to the j times minus 6 times 2 pi over 30 t. And then I will have b over 2 times e to the j times 5 times 2 pi over 30 t, and plus b over 2 times e to the j minus 5 2 pi over 30 t. Okay. Now it's clear because this is C sub 6, where 6 is coming from here, is equal to a over 2. And similarly, C minus 6, negative 6, is equal to also a over 2. And C5 is equal to b over 2. And C minus 5 is equal to also b over 2. Now, is there any question for that? Are we happy with it? As you see, there's no C1, there's no C0, there's no C minus 1. Even C2 and C3 and C4, they don't exist. So the fundamental harmonic does not exist, but the fundamental frequency is 2 pi over 30. So everything is an integer multiple of that. And I must insist on the accuracy of these indices, 6, minus 6, 5, and minus 5. For instance, in an exam question, if I ask you this kind of a question, or you encounter a similar situation, and you find the Fourier series coefficients in value, what are they? A over 2, A over 2, B over 2, B over 2, 4 values. The values may be correct, but you will get nothing. If you cannot say that A over 2 is actually C6, and C minus 6 is also A over 2. If you say C1 is A over 2, that's a wrong answer, because clearly C1 is not A over 2. C1 is 0. It does not exist. C2 is 0. C0 is 0. C minus 1 is 0. All right. So this was a critical observation that you have to make. You have to be comfortable with the Euler's expansion, and in case some phases occur in the cosine or a sine, so the C sub case will be containing complex exponentials or complex terms in general, real and imaginary parts. For sinusoids, it will be purely imaginary without a phase. Without a phase, for cosines, it will be purely real, but there may be any kind of a phase. And the ordering is very important. The index of the Fourier series coefficient is very important. And you may want to, for instance, plot this over the K or omega axis. It may be either of them. I may ask you to plot this over the K axis, or I may want you to plot it over the frequency axis. If it is on the K axis, then it will be like this: 0, 1, 2, 3, 4, 5 is A over 2, and 6, sorry, 5 is B over 2, excuse me, and at 6 it is A over 2. And all the others are zeros, and minus 1, minus 2, minus 3, minus 4, minus 5 is again B over 2, and at minus 6, it is again A over 2, and the others are zeros. So it's gonna look like this. You have to give me this kind of a plot. Well, of course, depending on the value of A and B, the plot may look different. The alternative of this one is to plot everything on the frequency axis, and over there you have to indicate where is omega 0, and that is 2 pi over 30. By the way, it's here, and the others are twice, 3 times, 4 times, and 5 times. So that's the same thing. It is 5 omega 0 that we have here, and the value is b over 2, and at 6 omega 0 frequency, the value is a over 2, and the others are zeros. 3, 4, 5, and 6. No, this is b over 2, and this is a over 2. At minus 5 times omega 0, and this point is minus 6 times omega 0. So either of the representations will be the correct representation for the Fourier series representation. Okay? Any questions here? Because this is critical. And don't tell me that you did not understand, I mean, or you haven't understood. Or if you didn't understand, you have to tell us why or what is missing right now, and do not say it after the exam. So don't complain after the exam. It's important. The indexing, be careful. Every index is an integer multiple of a fundamental frequency, fundamental periods inverse, 2 pi over fundamental period. Why B is taller than A? Well, I don't know. I just illustrated. The thing is that to the left-hand side and right-hand side, they have to be at the same length because they are the same B over 2. I just thought of it that way. It doesn't have to be. Of course, these plots depend on what the value, actual value of B and A is. I just made an illustration. It's not a value.
Hocam bir soru sorabilir miyim?
Yes.
Hocam XT'nin öğeler açılımını yaptığımızda oradaki indeksler 6, eksi 6, 5, eksi 5 çıktı ya.
Yes.
Sadece onlar çıktığı için diğerlerinin hepsini 0 aldık, değil mi?
Yes, of course. If you don't have any harmonic over there, it automatically means that the coefficient, the Fourier series coefficient corresponding to that non-existent harmonic is 0. That's why it doesn't appear, because the coefficient is 0. It is 0 times e to the j, for example, 20 times 2 pi over 30t. So C20, C sub 20 does not exist. It means C sub 20 is 0. Okay.
Evet hocam, teşekkürler.
All right. Now, we will briefly come back to, or we may encounter other examples of sinusoids, but right now I will open a new page, because I want to talk about something else now. The reason why we are writing our x of t as in the form of complex exponentials or complex sinusoids, in other words, like a1 e to the j omega 0 t. I'm going to write it again, plus a2 e to the j 2 omega 0 t, plus a3 e to the j 3 omega 0 t, plus etc. Why are we writing it this way? Of course, there may be negative exponentials as well, negative frequencies as well. Signal into some combination of impulses. Why were we using impulses? Because for linear and time invariant systems, we had impulse responses. So if you have response to this impulse, then what will be the response to the next impulse? It will be this impulse response. Because of linear and time invariant properties, when you shift the impulses, the responses were also being shifted. And when you scale the impulse, input impulse, the responses are also scaled the same way, which helped us to develop a method for decomposing our input into impulses, and therefore finding the output of the system to that input by using convolution. How are we doing that? We were convolving the input signal x of t or x of n with the impulse response h of t and h of n, and we had the formula for that. So convolution requires impulse responses. All right. However, these are not impulses. These are different complex exponentials. There must be a reason why I am trying to decompose my signal, not into impulses, but into harmonics, complex exponentials at different frequencies. And that is because of a fascinating property of, again, linear and time invariant systems. You take one of them, okay, one complex exponential, let's say e to the j omega 0 t. So it doesn't depend on omega 0. Just leave it as omega if you wish. It's just the frequency. Regardless of the frequency, if you input this to a system with an impulse response of h of t, the output will be a complex number a, which depends on the frequency of the input, omega 0, or maybe I should write it like this. It is a function of omega 0. It depends on omega 0, but it's just a complex number times the same harmonic. That's nice. It is telling me that if you input a complex exponential, almost the same complex exponential goes out of the linear and time invariant system, only scaled by a complex number, sometimes real. So it is also telling me that if I have a summation of ak times e to the j omega k t for all k as the input to a linear and time invariant system, then the output is the same summation. Because of linearity, I can scale the complex exponential by ak, and the output will also be scaled by ak, and I can combine two complex exponentials in the input. That means I'm combining the responses corresponding to those two exponentials at the output. And for each exponential, complex exponential, the response is also a complex exponential. It is a omega k times a sub k e to the j omega k t for all k. So whenever the input is this, the output becomes, that same input appears here, first of all, and it is scaled by the corresponding scalar, which we don't know yet, but we will soon discover what a of omega is, capital A of omega is. Depending on the frequency, what is that a of omega 0 thing? If you can find a formula for that, or if it is given to you, then it is telling me that it will be very easy for us to find the output or the response of an LTI system when the input can be decomposed or split into complex exponentials, because we know the response to each of those complex exponentials. But what is this a of omega 0? And that it's not very difficult. It's not as difficult as you may suspect, because it's actually, we know that if a to the j omega 0 t going into a system with impulse response h of t, if you think of it that way, we know that the output is e to the j omega 0 t convolution with h of t. So do not hesitate to write the formula for the convolution. And the convolution is integral from minus infinity to infinity h of tau x of t minus tau. It could be x of tau h of t minus tau, or h of tau x of t minus tau. It can be in both ways. You know, we know that you can interchange the positions or the roles of two convolutional signals. One of them is h of t, the other one is x of t. Here, x of t is e to the j omega 0 t. So the convolution can be this convolution this, or this convolution this. So I'm going to write it like this: h of tau x of t minus tau, which is e to the j omega 0 t minus tau theta. Okay? And from there, integral h of tau e to the j omega 0 t. It's coming a little bit slowly to my window, so I'll be waiting. I will just wait for the internet to stabilize a little bit. We have some problems. Okay, so e to the j omega 0 t term over there is independent from the integration variable. The integration variable is tau, and this is t, so I can take it out of the integration and write it like this. E to the j omega 0 t times integral from minus infinity to infinity h of tau e to the minus j omega 0 tau theta. Now, you may believe it or not, but as you see, this is the same as the input, and I have an extra term here, which is a of omega 0. Can you see that it's only a function of omega 0? Because there seems to be some taus also happening inside the formula, but it's just an integration variable. So when you integrate with a definite integral, with upper and lower bounds, we have nothing related to tau. So all of that will be a function of omega 0 only. So it is, the right-hand side integral is a of omega 0. So I can easily say that, therefore I found a of omega 0 times e to the j omega 0 t, where a of omega 0 is this integral. But this time I'm going to write the integration from minus infinity to infinity a little bit different, because I'm having difficulty in writing tau. So let me not write tau. Let me use a different parameter. Let me use t, h of t e to the minus j omega t dt. It's the same. I just replaced the tau term with t, because t will not appear in this at the end of this integration anyway. At the end of the integration, it will be a function of only this omega 0. And furthermore, from here, I'm going to change the notation a little bit, and I'm not going to call it a of omega 0, but I'm going to call it h of omega 0, because everything is described by h of t, the system, impulse response of the system, and it depends on omega 0 as well. So h of omega 0 is from minus infinity to infinity h of t e to the minus j omega 0 t dt. And furthermore, since this is a valid formula for all omega 0s, why don't I simply say that h of omega for all omega 0 means for all frequencies is equal to the same integral h of t e to the minus j, not omega 0, but every omega t dt. All right, this is called, the frequency response of the linear and time invariant system. Why am I calling it frequency response? Because the response is determined by the frequency, omega. It's not the impulse response, but it is generated from the impulse response with this formula, with this integral formula. And this formula, although it's not our chapter's topic yet, when we go there, you will already know this information if you're listening carefully. This formula is also known as the Fourier transform from h of t to h of omega, to capital H of omega. It's, capital H of omega is the Fourier transform of h of t, in other words. And this Fourier transform formula, although we found by just convolving and looking at what's the meaning of that frequency-dependent parameter a of omega 0, we started from there, but eventually we came up with the, we derived the formula for the Fourier transform, starting from the convolution. And it's valid, it's a valid expression for all h of t. You can just replace that h of t with any signal, let's say g of t, x of t, y of t. It will give you the corresponding Fourier transform. So Fourier transform of x of t, for example, will be capital X of omega with the same formula. Instead of h of t, you just put x of t instead of h of t. Okay, so why are we using it again still, and how are we gonna use it? Let me open a window from here. Let me use this space a little bit more. Suppose that we have this Fourier series representation that we found. One of you guys asked, why is b over 2 taller than a over 2? I don't know, but let's give some numerical values to them now. Let's assume that these CKs that you find from the Euler's expansion or something like that have these values at 0, 1. It's not 1, it is omega 0. This is 2 omega 0. At 3 omega 0, suppose you have 2. This is 3 omega 0. And at 4 omega 0, let's assume that you have a value 3. And others at 5 omega 0, 6 omega 0, 7 omega 0, etc. They are all zeros. And let's assume that they are cosines. So this is the same 2, and this is the same 3, and it goes symmetrically. As a matter of fact, for all real periodic signals, the Fourier series coefficients will have to be at least conjugate symmetric. So the real parts will be completely symmetric. If it is imaginary, they will be conjugate symmetric. Do you remember the Fourier series coefficients from a sine? It was a over 2 j and minus a over 2j, because they are imaginary, purely imaginary. So one will be the negative of the other one. One will be upwards, the other one will be downwards, or positive and negative. But that's because they are imaginary. For conjugate symmetry, the imaginary parts must be negatives of each other, and the real parts must be the same. That is what we call conjugate symmetry. And these Fourier series coefficients are always conjugate symmetric for normal real life signals. And let's also say that omega 0, let's give a value to that. Omega 0 is, let's say, is 2 radians per second. Okay. And now I have a frequency response of a linear and time invariant system. So I'm drawing h of omega. And somehow it is let's say 1 at the peak, and at 10 it goes down to 0. This is minus 10. Why did I plot it like this? Because I'm assuming that it's given this way. This is just one example. So you know the frequency response. You are given the frequency response. Maybe in the exam question, I will just plot some known shape. By saying known shape, I mean at any point of the frequency along the frequency axis, if I give you the frequency, it must be easy for you to determine the corresponding value. So this is, by the way, 5 omega 0, because omega 0 is given as 2. So we know, for example, what the value is at 4 omega 0, which is 8, and 3 omega 0, which is 6. So what is the value, for example, at this point? It is 1 over, or 2 over 10, which is 1 over 5. This value is 1 over 5 from geometry, okay? And this value here is 2 over 5. Do you agree with that? Is there any question up to so far? I'm just evaluating the value of that h of omega at some given omega values. This is just an example, as I say. Now the question is, if x of t goes into h of t, what is y of t? And by the way, this x of t from these Fourier series coefficients, I can say that it's equal to 4 times cosine omega 0 is 2, so 2t plus 6 times cosine 3t. No, I'm sorry. This is so very, very incorrect. Because if I say it like this, then omega 0 will be only 1. Omega 0 will be 1 for my answer, this one. And these will be the second and the third harmonics. So it has to be different. They must be cosine 6t plus 6 cosine 8. It's ugly, so let me erase and correct. 8t. Yes, more like this one. I could ask the question, for starting from this cosine expression, I can ask you, what is the fundamental frequency? And what are the Fourier series coefficients? And you must tell me that the fundamental frequency omega 0 from here is 2, because 6 is 3 times 2 and 8 is 4 times 2. So the common divider for all of them is just 2. That is the fundamental frequency. And for that, I have the third Fourier series coefficient corresponding to 4 over 2, which is 2, and the fourth coefficient corresponding to 6 over 2, which is 3. So C3 is equal to 4 over 2, that is 2, and C4 is equal to 6 over 2, that is 3. Of course, there is C minus 3 will also be equal to 2, and C minus 4 will be equal to 3, which is what we have here in this graph. So the input is this, and h of t is not given in the form of an impulse response. Instead, I'm giving you the frequency response, okay? H of omega. I'm giving it to you in the examination. I'm drawing, or I'm giving an expression to that. So you know the values of h of omega at each and every omega. The question is, what will be the outputs? The outputs will be behaving like this. Let me extend it a little bit like this. Here I have C3, C minus 3, C4, C minus 4, and these will have this y of t will have the same frequency, fundamental frequency, and the same harmonics. Why is that? Because every time a harmonic enters into a linear and time invariant system, the same harmonic goes out with a different scale. So I will have D3, D minus 3, D4, and D minus 4, which are the Fourier series coefficients of y of t. And the relation between dk and ck is that dk is equal to h of omega at omega is equal to k times omega 0 times ck. So I will just have to multiply every Fourier series coefficient with the corresponding frequency response, because every Fourier series coefficient corresponds to a frequency, and the frequency response at that frequency is h of omega at omega is equal to k times omega 0, that particular frequency. So I have to multiply ck with that value. So from here, from this question, can you immediately tell me, for example, what is D3? Let's write them in bold green. D3 is equal to h of omega at omega is equal to 3 times omega 0, which is 6 basically, times C3. And that value is h of omega at omega is equal to 6 is here, this value. That is 2 over 5. 2 over 5 times, what is C3? Let's look. C3 is 2, okay, times 2. So the value is 4 over 5. So we found a Fourier series coefficient of the output, D3. And we are going to do it for all of the Fourier series coefficients. Like D minus 3 will also be, by the way, 4 over 5. That's easy. D4 is equal to h of omega at omega is equal to 4 times the fundamental frequency, which is 4 times 2, that is 8. Omega is equal to 8 times the value of the corresponding Fourier series coefficient, that is C4, and that is 3 times C4. So h of omega at omega is equal to 8 is 1 over 5. It is this value, 1 over 5 times, and C4 is 3. So the answer is 3 over 5. This is D4. And D minus 4, you just do the same, or from symmetry you may inspect that that is equal to also 3 over 5. So now I have, this is D3, D minus 3 is here, this is D4, and D minus 4 is here. So I will combine all these 4 expressions to construct y of t, the output. Y of t will then be equal to, let's start from D3. It is 4 over 5 e to the j 3 times omega 0, that is 6t, plus 4 over 5 e to the minus j 6t, and that is from d minus 3, plus 3 over 5 e to the j 8t plus 3 over 5 e to the minus j 8t. I can simplify it a little bit. I can clearly see that in couples they correspond to cosines. In case you may not notice this, that's fine. I mean, you may lose just 1 point or something like that. There must be a difference between those who can simplify it further. This is with a 1/2 factor, like 1/2 e to the j alpha t plus 1/2 e to the minus j alpha t, which makes a cosine. But to compensate for the 1/2s, I must multiply by 2. That makes an 8/5 cosine 6t, and this makes a 6/5 cosine 8t, and the summation is phi of t. So this is the answer, which is the output, if the question is given like this. Now, let me make it a little bit smaller and come back to these original figures. So what I'm really doing is I'm multiplying every Fourier series coefficient, for instance, this one, with the corresponding value of h of omega at the same frequency. Or this one, I'm multiplying with the corresponding frequency, this one. So they are totally aligned. Of course, I couldn't plot it that way, but they must be vertically aligned, of course. The same frequency correspondence is just scaling those corresponding Fourier series coefficients. For instance, this 3 here is scaled by this value, and this value 2 is also scaled by this value here. Okay, that's what we are essentially doing, which makes the bottom shape, this thing, h of omega, to be actually a frequency selective or frequency behaving filter. This is a filter. As you see, for instance, let's analyze this particular filter example. It is showing some frequency characteristics. For lower frequencies, it is scaling closer to 1. But for higher frequencies around the tails or towards frequency going to infinity, it is first reducing and then staying as 0. It's not passing the very high frequencies. For all frequencies above 10 radians per second or beyond minus 10 radians per second, everything towards infinity, this thing is not passing at all. It's just making them completely 0. So, for example, if there could be any Fourier series coefficient here and correspondingly here, those two red points, they would be completely eliminated, and the output will not contain them because 0 times that Fourier series coefficient value will be 0. So the output Fourier series coefficient will be 0, which means it doesn't exist. So those harmonics will be completely eliminated. So this one is eliminating high frequencies, this shape. Other shapes may also eliminate high frequencies, but there may be some different things. For example, you can say that, or let me give you some examples here. For example, can you give a name to this kind of a filter which just passes everything between W and minus W alongside the frequency axis as 1 or any scale, it doesn't matter, and all the others are zeros. So it's completely eliminating high frequencies, and it's passing only the low frequencies. So what is the name of this filter? Can you tell me a name, give a name to this one?
Low pass.
Low pass, exactly. This one is low pass filter. And that's exactly what it is doing. It is passing the low frequencies. Here it is. The harmonics corresponding to lower frequencies are being passed with this one. Shapes may be very different. Some filters you cannot give names, but these are very typical filters whose name you should better know. For example, this one is a very typical, it's an ideal low pass filter, by the way. It's very uniform. The top one here, this triangle shape, is also a low pass filter because it is passing the low frequencies and it's not passing the high frequencies, but it's not ideal low pass filter. Let's think of alternatives. For instance, this filter, starting from W1 and minus W, extend this value is 1 or any scalar, and it's not passing the low frequencies. So what is it in name? High pass. It's a high pass filter, actually. And of course, we may have even more interesting things. For instance, it may be from W1 to W2 and symmetrically from minus W1 to minus W2. And the name for this one is
bandpass.
Bandpass filter, exactly. Okay, another example, still we can go. How about this one? Band stop, exactly, British. We have been using pass names previously, but this one is particularly stopping some frequencies and some band of frequencies between W1 and W2, and therefore this is a band stop filter. There are alternative names to this one due to some reasons, historic reasons. For example, these are also known as band reject filters. They are just the same things. Reject filter. And the most historically oldest name is the notch filter. This is, although the shape is not really notch, it's an extension of that notch shape, therefore people just use it that way. The notch filter, this one, essentially looks like this. Like this. That shape is a notch. When you kick with an axe, okay, you make a dent, and the shape of that dent is notch shape, and because of that they use notch filter. In audio systems, for example, a practical application of this one, in audio systems, since there is 50 hertz everywhere in Europe and in Turkey, it may be different frequencies in other places like Americans using 60 hertz. That frequency becomes audible. You start listening to a hum, a very low frequency, 50 hertz, and it is added into your audio, and you just apply this kind of a notch exactly right. Okay.
Well, okay. So,
I'm just gonna.
all right. Obviously, the system is trying to tell me that it's been too long anyway. so let's stop at this point, and we will continue later with the other things. Are you hearing me now? Right? You can hear me now?
Evet hocam.
Okay. But I have to reconnect everything. So it's time to give a break. What time is it? It is already 3 o'clock. Let's give a 15 minutes break. Let's start at 3:15. Okay. At 3:15, we will meet again and do the second class. So I'm stopping at this point. We will continue from where we have been left. Okay. See you then.